Hello, and welcome to The Explainer. Today, we're diving into a hidden process, one that connects the very screen you're watching this on to, well, a bag of potato chips. It's a technology that makes so much of our modern world possible, and it's called sputtering. So let's start with a bit of a mystery. See, the everyday objects all around us are covered in secrets. Specifically, these invisible, ultra-thin layers that give them some of their most amazing properties. So what is the connection? What could a high-tech piece of glass possibly have in common with a snack food? Well, the answer reveals one of the most fundamental technologies of the 21st century. And there it is, sputtering. It's the process of depositing an incredibly thin film of material onto a surface. It's the invisible link that creates both the anti-reflective coating on your screen and the metallic barrier inside the bag that keeps those chips fresh and crispy. Okay, so how does this incredible process actually work? To get it, you really don't need a PhD in physics. All you need is a little imagination and a trip to an atomic scale pool hall. At its heart, sputtering is a physical process, not a chemical one. The best way to think of it is like a hyper-precise atomic scale sandblaster. But instead of blasting away with sand, you're using individual ions. And you're not stripping paint, you're gently knocking atoms off a source material in order to build something totally new. This atomic billiards analogy is really the perfect way to picture what's happening. It is all about transferring momentum, just like a cue ball smacking into a rack of balls to get a very, very specific result. So in this game, we've got three key players. First, there's the target. This is the solid block of material we want to make our thin film out of, like aluminum or titanium. Second, you've got the substrate. That's the object we actually want to coat, like a silicon wafer or a lens. And finally, you have our atomic cue balls, which are usually atoms of an inert gas like argon. The whole process plays out in a few steps. First, you start with a vacuum chamber and fill it up with a little bit of argon gas. Then, you hit it with an electric field, which ignites the gas into a plasma. That's the cool purple glow. This strips electrons from the argon atoms, creating positively charged ions. Next, those positive ions get accelerated by the electric field, and they slam into the target material. Finally, that impact knocks atoms loose from the target. They fly across the chamber and deposit themselves onto the substrate, building up, atom by atom, into a perfect, ultra-thin film. And this right here really shows the billiards part perfectly. Look at that. One incoming argon ion doesn't just hit a single atom and knock it out. No, it sets off a whole chain reaction under the surface, what's called a collision cascade. All that momentum gets transferred around until finally, an atom right at the surface gets enough of a kick to break free and get sputtered. Now, just like any sophisticated game, sputtering isn't a one-size-fits-all process. There's a whole playbook. There are different strategies and different types of sputtering, depending on what kind of material you're working with. Let's look at the two main plays. On one hand, you have DC sputtering. It uses direct current, it's fast, it's simple, and it's perfect for materials that conduct electricity, like metals. Then you have RF sputtering. This one uses a radio frequency and alternating current. It's a bit more complex, but its huge advantage is that it can coat anything, including insulators like glass or ceramics. You can think of DC sputtering as the economical workhorse. If you just need to lay down a simple layer of metal, it's the go-to method. But it has one big weakness. If the target itself isn't conductive, a positive charge builds up on the surface, and the whole process just grinds to a halt. So what happens when your target is an insulator, like the ceramic material for a high-performance coating? You can't use DC. And this is the exact problem that RF sputtering was invented to solve. By rapidly flipping the electric field back and forth, it never allows that positive charge to build up. This simple trick lets us sputter literally any material we want. Then, as if that wasn't clever enough, came a brilliant innovation, magnetron sputtering. Think of it like a turbocharger for both DC and RF systems. By simply placing powerful magnets behind the target, you create a magnetic field that traps electrons right near the surface. This means way more collisions with argon atoms, a much denser plasma, and a dramatically faster coating speed. It was a total game changer, making everything faster and much more efficient. Okay, so we've looked at the physics, we've played some atomic billiards. Now let's zoom back out and see how this atomic scale process actually builds the world around us. Because the applications, they're truly mind-blowing. I mean, just listen to this list. Every single microchip in your computer is built with sputtered layers. The anti-reflection coatings on your glasses, The thin films in solar panels that generate electricity, the data layers on CDs and hard drives, those super hard coatings on drill bits, even biocompatible layers on medical implants, all of them are made possible by sputtering. This is such a great way to picture its impact. What started out as just a curious bit of research in nuclear physics has grown into this massive tree of modern technology. You've got branches reaching into medicine, microelectronics, data analysis, and so much more. Sputtering isn't just one of the branches, it's a huge part of the trunk of that tree. So let's wrap this up. We've gone all the way from a simple question about chips and phones to a truly foundational technology of our time. It's a process of incredible atomic-level precision that happens on a massive industrial scale. I think the key takeaway is this incredible paradox. Sputtering is a technique that meticulously removes atoms, one by one. But in doing so, it builds the high-performance films that are the very foundation of our entire high-tech world. And this leaves us with a final thought. Given how incredibly versatile this process is, the real question isn't about the thousands of things we already coat using sputtering. The real question is, what's next? What new materials, what new devices, and what new possibilities are we going to create with it tomorrow? What will we coat next?